Section 3.7 is titled Optimization. Optimization means finding optimal values of things. In particular, places where things are a maximum of some sort or a minimum of some sort. So you might think about just real life practical kinds of things. If you were running a business, what component of your business might you want to maximize? Profit, right? Profit is the thing that you actually take home at the end of the day. Maximize profit. In that business sense, what might you want to minimize? Expenses or your costs. So there are different situations when we want to maximize or minimize certain quantities, and that's just a business example. There's lots of science kinds of examples as well where you're wanting to maximize or minimize things. So I know that when I drive to work in the morning, I'm trying to minimize my time. I don't really even care about the distance, right? If I can minimize my time, it might be worth driving further to do that sometimes. And your phone maps do that, don't they? They minimize time usually for you, give you some of those options. All right, so here's the general idea, some guidelines for optimization. The first one is to make some kind of a visual. This doesn't always happen, but most of the time there's some kind of a visual that will help you with your problems. Sketches, tables, graphs, things like that. Number 2 is to identify what you know and what you need to find. Right? And then 3 is usually making equations that relate those ideas together, the things you know and the things you need to find. What you want to maximize or minimize, that's optimize. And that step also includes getting some kind of an equation where you only have one variable in it. Right? Like if you think about an area equation of a rectangle, area is length times width. Well, L and W are 2 variables. I don't want 2 variables in the equation. Somehow I want to make sure that there's only one. Number 4 is to determine the maximum minimum allowable values. Right, so if we're talking about costs and expenditures on a business, the minimum would be 0 on any of those kinds of things. I can't have negative cost, right? I could, however, have negative profit. That would be really bad, right? That wouldn't be a good situation for you to be in, but it's a possibility. So it's not necessarily like all positives or all negatives are out. It really depends on the context that you're looking at. And then the 5th one is where you use the calculus that we've been doing up until now, basically sections 3.1 to 3.4, to actually find the maximum and the minimum and apply that in the context of the problem. So we're going to do an example. This is a very standard kind of an example. There are other ways to do this with non-calculus techniques, but I'm going to show you how the calculus looks for this particular problem. Okay? So, just a second. All right, let's get back started. All right, so we have this one. A 3-sided fence is to be built next to a straight section of river, which forms the 4th side of a rectangular region. The enclosed area is equal to 1,800 feet squared. Find the minimum perimeter and the dimensions of the corresponding enclosure. So this is one of those ones where that very first step makes a lot of sense. Drawing a picture of this is a perfectly legitimate kind of thing to do. We've got a section of river. There's my river. It's even blue. How do you like that? All right, and then we're going to draw a 3-sided fence. So there's not going to be a fence along the river itself. So imagine that you're sort of enclosing, maybe you're going to be pulling a boat up into this area or something like that. So that's why you're on the river. That's the best I can come up with for why we would be on the river. But we're on the river. All right, so we're going to enclose a fence around this piece, and it's going to be a rectangular fence where one of the sides of the fence is sort of the river. So it looks something like that. Good so far? Tell me what you know about this enclosure. The area is, what do you say? Okay, so they tell us the area. My pen is not cooperating very well. It's 1,800 feet squared. What else do we know about this enclosure? And it may not be in the problem. I mean, maybe prior knowledge kind of things. What else do you know about this shape? We'll say it that way. Okay, so there's a formula for this shape's area called length times width, which we will use that in a moment. We'll need that. What else do you know about this shape? There's at least one more fact I know you know about this shape. It could be a square, that's true. Not what I was going for, but you're correct that it could be a square. Tell me what you know about the top of the rectangle and the bottom of the rectangle. They're the same. That's a really important piece of information for the problem. Nope, not too simple. We do want to have that in here. The reason that matters is because we want to write that down. So we'll call that our width. Is that good with you guys? So this is a W up here, and this is a W over here. And then the side over here, it may or may not actually be the same, right? Like Josh said, I mean, it could be that it's actually a square, and that's the same value. We don't know that. So these are my different values in my rectangle. What is the goal of this question asking me to do? I mean, like, what's the point? Yeah, it's about perimeter because I'm trying to minimize, yeah, something about the fencing, right? Minimize the fencing, usually because we've got to deal with cost, right? You don't want to have more fence than you need. All right, so can you give me one more equation that's present in all of that sort of language that you guys just worked through? Right, P equals 2W, say that again louder. Plus L. Why isn't it 2L? We don't have to pay for fencing on the side of the river. Is everybody good with that? So this is not necessarily the perimeter of a rectangle, it's the perimeter of the shape I'm working with, which is a three-sided rectangle. It sounds kind of funny, but you know what I mean? Okay, so we have two equations. These are my two equations. Hang on, let me write it differently. We know that the perimeter is 2W plus L. We know that the area is length times width, and that's also equal to 1800. And I think that means that, wait, no, we have one more step before that. I was about to jump the gun. It says on number, no, I was on number 4 actually. Yeah, so on number 3 it says that what we're going to try to do is we're going to try to write one equation in one variable, because now I've got two equations and two variables. So what am I going to have to do in order to write this as an equation in one variable? Exactly. Do you know which equation I can solve, Nathan? Yeah, hang on. Let's try to mark that. This one, right? This one we actually know it equals 1800. The other one we don't have it equal to a constant, correct? So this is the one that I'm able to solve for one of the variables, and it really doesn't matter which variable I solve for. So what was your suggestion? L. Okay. So L is going to equal 1800 divided by W. Is everybody good with that? And then I'm able to take that quantity for L and plug it in the other equation for L. So my perimeter now has the equation 2W plus 1800 over W. Okay? There's one other thing that we're going to do before we start using the calculus. That's step 4. Talks about maximum and minimum allowable values. So think about the shape that we're dealing with here. What's a minimum that I can use for any of my sides of this? Yeah, technically, something smaller than, something bigger than 0 is what I need, right? So we really do need our W to be greater than 0, our L to be greater than 0. And, if you said it's 1, I get what you're saying. Technically, could you have an enclosure that's a 1/2 on one of the sides? Wouldn't be very wide, right? It'd be pretty narrow. Not anywhere to walk, but yeah, technically you could. The other upper end of that's a little trickier, though, because if, say, for instance, you use the number 1, pretend for a moment that this is 1, and this is 1, then what would L be? 1800, right? But what happens if those 1s are 1/2s? You can actually use it at 3600, right? So since there's really not a lower bound that's a specific number that's non-zero, it's very hard to say what the upper bound would be. But what we could say is something like these are hard and fast rules. We cannot have any negative numbers here. Everybody agree with that? Definitely not going to happen. Can't have zeros. But we can say something like this, that W and L, and there's not a symbol for this, these have to be something around less than 1800. So these are approximates. We're looking for values that are something around, or something between 0 and 1800. Those seem reasonable, right? Okay. So if you end up getting an answer in here that's 55,000, and you start looking back at how big the other quantities have to be, you might be thinking that doesn't make a lot of sense. Everybody good at that? Okay, good deal. So these are sort of a lower end and an upper end bounds on our variables. We are ready next to do some calculus. And what's the calculus we're going to have to do to this equation? The derivative. The derivative will tell us how we can get a maximum and minimum value for a function, right? We said to find the derivative, set it equal to 0, and solve. Is there a different way I can write this that would be more helpful for finding its derivative? Yeah, 1800 times w to the negative 1. All right, so here's my equation. Yes, I realize there's an extra w hanging out up there. I'm going to remove him. Okay, and we need to find the derivative. So somebody help me out. What did you get for the derivative of this function?
2 minus 1800 over w squared.
Okay. And Caleb went ahead and switched it back into a rational function with the w squared on bottom. Is everybody good with that? It's to the w to the negative 2, and then put back in the bottom. And we need to set this equal to 0. You have to be really careful because it's really tempting to say, oh, well, it can't ever equal 0 because I've got a fraction, but you also have that whole number part. So that if you were to get a common denominator or something like that, you are going to be able to get this to equal 0. That's a possibility. So what I'm going to do is I'm going to get this to have that denominator. So I have 2w squared minus 1800 over w squared equals 0. How do I find out where this equals 0? What do I have to do? Yeah, it's all about the numerator. And there's another thing we could have done that I didn't choose to do it in that way. But another possibility is when I actually did that w squared on top and bottom, I could have just multiplied the whole equation through by w squared. And I would have immediately gotten to this last step right here that I'm on right now. So just a couple of different ways of thinking about that. All right, so now what? Okay, so what's my first step in solving for w? Huh? That sounds great. So we're going to do 2w squared equals 1800. And then what? Divide by 2. So I have w squared equals 900. What will w be? Yeah, technically it's plus or minus 30. Of course, that's not really what we have here, right? What one is it really? Well, it would have to be the positive because we know that we can't have a negative with the fact that this is a width, right? No negative widths. Here's the catch. It feels like at this point you're done with the problem. You've got w equals, but you need to confirm that it really does find the maximum or the minimum because occasionally you will have found the thing you weren't supposed to find. Like it was telling you find the maximum and you just found the minimum value. So you need to confirm that you found the right one. So how do you do that? Well, how do you figure out if a value is a maximum value or a minimum value for a function? Number line. Number line's a good way. That's the first derivative test. We'd have the 30 in here, and then what would we do? Yeah, a number smaller and a number bigger. So maybe we decide to do 10 and 40. I don't know. Some number before it, some number after it. Really, we should stick with numbers bigger than 0, because realistically in our function it doesn't make sense to plug in 0. We've talked about that, right? Where are we going to plug the 10 and the 40 in? The derivative equation. So, like the one, oops, I didn't mark it right. Oh, I don't even have it in here anymore the same way. This right here, where I have the 2 minus 1800 over w squared would be a good place to do that, right? So if I plug in a 10, do I get a positive or a negative? A negative. And if I plug in 40, what do I get? You actually get a positive when you plug in 40. So this is a negative and then a positive. So what is this point right here at 30? What is it? A minimum, right? Is that what we were looking for? Yeah, minimum perimeter, right? Okay, are we good so far? Okay, we're going to finish up this problem by answering the question that was asked. Because also, just because we found W equals 30 doesn't mean we've answered the question that was asked. It wants us to find the minimum perimeter and the dimensions of the corresponding enclosure, and 30 is neither one of those things. So, if W is 30, like so, what will the L be? What'd you get? Thought I heard somebody say it. 60, that's right. Very good, Marco. How did you get 60, Marco?
Divided the area by the width.
Right. The area was 1,800. We have this relationship right here in the middle, right, that says that the length is 1,800 divided by the width. So it would be 60. So what is the minimum perimeter, or another way of asking it is, how much fence do I need? Remember, it's the perimeter of the object we're working with, not the whole rectangle. What's the perimeter? Yeah, it's 120. What are my units on that? Feet. It's a linear measurement. And then I want the dimensions. What are the dimensions of my shape? "30 feet by 60 feet. Or you can say 60 feet by 30 feet. That's reversible, doesn't matter. 8 by 10, 10 by 8 kind of thing, right? No big deal. All right, any questions on this first example? Does anybody remember, we're not going to do another example, does anybody remember another way of doing this problem without calculus? By any chance? Square root, what'd you say? Okay, so what would we do the square root of the 1,800 to find? I don't think if you square root it, you'll find the lengths of them, though, because the square root of 1,800 is not a whole number. What was that, Josh?
Exact number is like 42 point whatever.
But that wouldn't give me, how would I use that to find the 30 and the 60?
Oh, find 36.
Yeah.
It's just a find.
Yeah, that would be to find what makes it a square, is what you're doing. That would find a square, but we don't necessarily have a square. In fact, this one we didn't have a square. We actually have a rectangle, legit rectangle. This equation that you got on P, right there towards the bottom, either of these versions, it doesn't really matter. Could you graph it and look for where it actually has a minimum on your grapher? Yeah, you could. It would also confirm that the calculus that you did after that was correct, wouldn't it? You probably have to play with your window, because we did get a value for W that was 30. It's not going to be in that senior 10 by 10 window, so you probably have to play with your window a little bit to get that to happen. Sometimes you'll have equations that will actually end up being like a parabola, and you're looking for the vertex of a parabola. Do you know how to find the vertex of a parabola not using calculus? It's been too long. There are college algebra, there's an equation that says negative b over 2a for finding the vertex of the parabola. Of course, calculator will also give you a graph where you could, research that information. But there are other ways besides calculus to do it, but calculus works very, very nicely and very cleanly for a lot of these. So those are the ones that we're going to be taking a look at. We have 2 more examples for next time, but we'll stop here today.